Okay, I'm back. This is my first lecture, installment 2. And some other things that we have to review are the notions of particular solutions and complementary solutions. Now remember, if we have an nth order linear differential equation with constant coefficients, in other words, a sub n is constant, a sub n minus 1 is constant, and so forth, a particular solution is a function u of x, or just u, that is a solution of this equation. In other words, if we take u of x, or u, and all of its derivatives and plug them in for y and their derivatives, we'll get the right-hand side f of x. And by the way, I will use u and u of x interchangeably, u prime and u prime of x interchangeably. So when I have a u here, I'm talking about u of x and so forth. Let's look at this example. Y double prime plus 3y plus 2y, y double prime plus 3y prime plus 2y is 4x cubed plus 18x squared plus 12x. We can verify that u of x equals 2x cubed is a particular solution of the equation. In other words, when we take u and all of its derivatives and plug them in for y and all of its derivatives, we're going to get the right-hand side, 4x cubed plus 18x squared plus 12x. So here's u, 2x cubed. U prime is 6x squared, u double prime is 12x. So we're going to take u prime, and u double prime, and plug these into the expression y double prime plus 3y prime plus 2y in place of y prime, and y double prime respectively. So let's see. Where y double prime went before, we're putting u double prime. Where we had 3y prime before, we have 3u prime. And where we had 2y before, we have 2u. Now let's see what we get. We get 12x, check. We get 3 times 6x squared, which is 18x squared, check. We get 2 times 2x cubed, which is 4x cubed. Perfect. When we plug u prime, and u double prime in for y prime, and y double prime, we get the right-hand side, f of x, 4x cubed plus 18x squared plus 12x. So what we can say is u equals 2x cubed is a particular solution of the equation. There are other particular solutions of the equation as well. Okay, something to remember. Relative to the original differential equation, we define something called the complementary equation. Now let's see. Here's the original linear differential equation with constant coefficients. Here's the corresponding complementary equation. How do they relate to one another? Well, if we look closely, the left-hand side of each equation is the same. A sub n nth derivative of y, a sub n nth derivative of y, a sub n minus 1 n minus first derivative of y, a sub n minus 1 n minus first derivative of y, a2 y double prime, a2 y double prime, a1 y prime, a1 y prime, a0 y, a0 y. The only difference between the original equation and the complementary equation is that we set the right-hand side of the original equation equal to 0 to get the complementary equation. So, in terms of operator notation, if phi of dy equals f of x is the original differential equation, then phi of dy equals 0 is the complementary equation. Let's look at an example. y double prime plus 3y prime plus 2y equals 4y cubed, 18x squared plus 12y. In terms of the differential operator, it's d squared plus 3d plus 2y, that is second derivative of y, plus 3 times the first derivative of y plus 2 times y, equals f of x. Now the complementary equation is y double prime plus 3y prime plus 2y equals 0. Or in terms of the operator, second derivative of y plus 3 times second derivative of y plus 2 times y equals 0. In other words, phi of d times y equals 0. Now, according to my notes, here's where the plot begins to thicken. I don't know if that's really obvious or not, but we're getting to where we need to be. We are. Now, just some things that we want to recognize. If u is a solution of the original equation, phi of dy equals f of x, and v is a solution of the complementary equation, phi of dy equals 0, then guess what? If we put both of these together, the particular solution and the complementary solution, we get a particular solution to the original equation. And here's why that happens. If u is a solution of the original equation, phi of dy equals f of x, then that means that phi of du has to equal f of x. If we plug in u in place of y, we still have to get f of x. Now, if v is a solution of the complementary equation, phi of dy equals 0, then if we plug in v for y, we should get phi of dv equals 0. So, let's plug in u plus v where y was. In the original equation, we had phi of dy. For y, we're going to plug in u plus v. And remember, the derivative of the sum of functions is the sum of the individual derivatives. So we can essentially multiply u and multiply v by this differential operator separately. We can take phi of v times u and phi of d times v. Well, let's see. Phi of d times u, that's equal to capital F of x, because u is a solution to the original equation. And phi of dv, that's 0, because v is a solution to the complementary equation. So when we plug in u plus v to the original equation, we get f of x plus 0, or just f of x. So u plus v is a solution to this equation. That we plug in u plus v for y, and we're going to get f of x. Now here's our goal. Our goal is to find the general solution of the original equation, phi of dy equals f of x. This general solution will represent all particular solutions of the original equation, in the sense that a mathematical expression that is a particular solution of this original equation. Now let me say that again. A mathematical expression will be a particular solution of this original equation if and only if it fits the form of the general solution. So in other words, if a function fits the form of the general solution, then that function is a solution of this equation. And if a function is a solution of this equation, it fits the form of the general solution. So it's our goal to get the general solution, because that will tell us what all solutions of the differential equation will look like. Okay, the big picture. Here's how we get the general solution of the original equation, phi of dy equals f of x. First thing we do, we find the general complementary solution. That's the general solution to the complementary equation, phi of dy equals 0. Then we find any particular solution, u of x. And here's why we do that. It turns out the general solution of the original equation will be given by y of x equals u of x plus v of x. In other words, the general solution of the original equation is the sum of the general complementary solution plus any particular solution. So the general complementary solution v of x plus any particular solution u of x constitutes the general solution of the original equation, phi of dy equals f of x. So let's do this. I guess the first thing we have to do, since step 1 up here says find v of x, the general complementary solution, we need to find the general complementary solution. We need to know how to do that. So for linear differential equations with constant coefficients, the expression e to the power of mx, where m is a constant, is always a solution for some value of m. This function, for some value of m, will always be a solution to the complementary equation. Now, for the sake of illustration, let's consider the complementary equation that we had before, y double prime plus 3y prime plus 2y equals 0. Or in terms of the differential operator, d squared plus 3d plus 2y equals 0. Okay. Our complementary solution is v equals e to the mx for some value of m. Let's compute the derivative and the second derivative so that we can plug v prime, and v double prime in for y prime, and y double prime, and show that we really do get 0. So v is e to the mx. V prime, well, that's the derivative of the exponent, which is m, times e to the mx. And v double prime, that's the derivative of the exponent, which is m, times m, which is m squared, times e to the mx. These are v prime, and v double prime. Now, here's what we're going to do. We're going to plug these, v prime, and v double prime, into the equation y double prime, 3y prime plus 2y equals 0 for y prime, and y double prime respectively. So we'll plug v in for y, v prime in for y prime, v double prime in for y double prime. And here's what we get. V double prime, where we had y double prime before, plus 3v prime, where we had 3y prime before, plus 2v, where we had 2y before. And let's see what we get. Well, let's see. E to the mx is a factor of each term here, so let's factor it out. We factor out e to the mx, and that leaves us with m squared plus 3m plus 2. And this polynomial in m times e to the mx is 0. Now, there's only one way that we can multiply two real numbers together and get 0. One of them's got to be 0. So either this polynomial has to be 0, or e to the mx has to be 0. And guess what? E to the mx isn't equal to 0 for any value of x. So you know what that means. M squared plus 3m plus 2 is 0. And we call this equation the auxiliary equation. But wait a minute. M squared plus 3m plus 2, haven't we seen something like that before? Oh, our complementary equation, written in operator form, is d squared plus 3d plus 2y. You see it? Here's a polynomial in terms of m. Here's a polynomial in terms of the operator d. They're exactly the same equation. This polynomial in terms of m is exactly the same as that polynomial in terms of d. So our complementary equation, phi of dy equals 0, written in operator form, has the same polynomial as the auxiliary expression. Son of a gun. Here's the complementary equation in operator form. And phi of d is the same polynomial as this one. The only thing different is the variable. So the auxiliary equation and the complementary equation both feature the same exact polynomial. So from now on, in order to get the auxiliary equation, that's this thing, we'll consider the complementary equation, phi of dy equals 0, and then we'll immediately construct the auxiliary equation, phi of m equals 0. I think maybe this calls for an example. I think it does. Maybe not yet, though. We have the auxiliary equation, phi of m equals 0. So what? Well, remember what m is. M is a number such that e to the mx is a solution of the complementary equation. And look what we have, the auxiliary equation in terms of m. It's a quadratic equation. We can solve this for m. M squared plus 3m plus 2 equals 0. We factor this. So m is negative 2 and or m is negative 1. So which one of these, m sub 1 equal negative 2 or m sub 2 equal negative 1, yields the solution to the complementary equation? The answer is both of them do. E to the m1x, which is e to the negative 2x, and e to the m sub 2x, which is e to the negative x, are both solutions to the complementary equation, phi of dy equals 0. But let's not stop there. We can keep on going. As it turns out, any linear combination of these two solutions is also a solution to the complementary equation. So in other words, a linear combination of this guy and this guy, in other words, some constant c1 times e to the m1x and some constant times this one, e to the m2x, or c1 e to the negative 2x plus c2 e to the negative x. This is a solution for all values of c1 and c2. In fact, this thing right here is the general complementary solution. Okay, let's stop for a second.